Hello and welcome to part number 2 of our lecture on dimensioning power conversion systems. So in this part we'll look into choosing the system components. The art of engineering is, among other things, the competence in putting components together and picking up right components. So where do we find components? Of course, the primary source today is internet. It is web pages of the providers of those components, so the equipment, and all kinds of catalogs. So of course some dimensioning tools are coming and some automatic selection of components is coming. You can check at the web pages of Siemens or ABB, for example, but still primary source of information is a catalog of electric motors, catalog of frequency converters, transformers, gearboxes, and so on and so forth. So we start with what is needed to start dimensioning. What kind of initial data do we need to start with? So let's take again the same example as in part number 1, wind turbine, and look into the inputs for our task. So it will be mains supply voltage and frequency. So this is what we have here on the grid side. So what is the grid? Is it 50 Hertz or is it 60 Hertz like in America or in Japan, Australia, and some other countries? So usually in our part of the world it is 50 Hertz. Then the question is, what is the voltage? So is it 400 volts, what is quite typical in industry, or is it 11 kilovolts, as it could be in the wind park? 11 kilowatts means 11,000 volts, or something even higher like 33 kilovolts, and so on. So next thing is motor nominal voltage, motor generator. It's an electric machine. So what is here? What kind of motor are we going to use? If on the grid side we have, say, 11 kilovolt, so of course our transformer can help us to bring the voltage down to the level we need, to 400 volts, for example. And then this voltage will be the voltage of our motor. Next question is, what speed range we expect our motor to operate in? So since we have the gearbox here, we can always bring up the speed of the propeller turning. It's maybe 15 RPM, just 15 RPM, but we can gear it up from 15 here on the blades up to 1500 on the motor side. And since the wind is not constant, so it goes up and down, and there are some wind gusts. So of course 15 will be rated speed of the blade, and they can also turn at 10 RPM, 5 RPM, and of course then the motor speed will have to be, or the generator speed in this case, will have to be variable in this range. So there can be a couple of more input parameters of the system, like load power at maximum speed or overload requirement, like that. So in DriveConstructor you will find cases dealing with all this input data. So first let's look at the motor, what kind of parameters we use for picking up the right motor. So of course it is torque, it is rated speed or range of speeds, and quite some other factors as well. So motor thermal parameters, or how it behaves thermally, will very heavily depend on the speed range and low torques. So the motor, which can be quite suitable for running, say, at the rated speed of 1500 RPM, can be too little for running with the same torque at low RPM range due to, for example, cooling issues or some other issues. Some motors may have problems when being run in overspeed. So when we go beyond the rated speed and run at like 10 or 20% higher speed than the rated. So these things should be taken into account. Then overloadability, maximum torque. here. So we should remember about overloadability both below field weakening point and above field weakening point. Yeah, maximum allowed speed here. Usually it is bearings that limit the high-speed operation, because bearings are usually rated for the rated speed, and okay, maybe 5–10% above, but not like double the speed. So here we have an example of how a page from a motor catalog looks like. So let's see here. So it's cast iron motors. Cast iron is the frame material of the motor. IE3 is efficiency class. It's something like medium class. There is class with high efficiencies and class with low efficiencies. You will find this information in the DriveConstructor textbook. And on this page of the catalog, we have two rated speed, 3000 RPM and 1500 RPM. So 3000 RPM, this is for two-pole motor, P equal 2. And 1500 RPM, that is for four-pole motors. So you can actually see this information here. Basically, catalogs are quite well organized. At least I like ABB catalogs very much, but other catalogs are quite similar in structure. So what you will find here is powers on the left-hand side, and speeds. So you see all the speed numbers here are slightly below 3000, and you know this is because of the slip. And we are talking induction motor all the time. Also, I probably forgot to mention it or stress it in the part number 1 of this lecture. I was talking about induction motors first of all. Okay, so then we have slip, and the speed is a little bit lower here. Efficiencies, you can see the efficiencies are quite different at full load and partial loads here. So you see it first usually goes a bit up when we run at 75% of the load, and then goes down when we go to half load, and then it will go further down if we head for something like 30% of the load. Next column is power factor, quite useful information in many cases. Then it is followed by current and torque. So rated current is quite important, because this is the parameter which is used for matching the motor with a frequency converter. As well as rated torque is important, because it defines the torque in the shaft defines what kind of load we will be able to rotate. The data like weight are important, because when we optimize our system or for weight, we'll be looking at this. Moment of inertia may be also quite critical in some applications. For example, in DriveConstructor we will have a winch application, and their moment of inertia will be used. Now let's take a look at the inverter selection. So the criteria here are voltage, rated voltage of the inverter, like 400 volts or 690, or something low or higher than that. Then current, the current the inverter is able to deliver to the motor, as well as other factors like overloads, for example. So the main rule is the motor continuous current should be lower than inverter continuous current. So inverter should be able to deliver higher current than what the motor needs. And for cases like with variable loads, it is more complex, so then we should look into these equations here. Like inverter duty cycle base current should be higher than motor continuous load current, and the same is true for maximum load current. This is how some parts of catalogs of frequency converters look like. There's FC's frequency converter. So this is the frequency converter and its outer dimensions. And here we have frame sizes with some designations. This is again ABB catalog, R0, R1, and so on, with dimensions and weight. Here you can see it. And also we can went had efficiency class, that's protection, weather protection against dust and water. This knowledge is useful for when selecting converters. Now another table from the same catalog, so you can see frame sizes are here. So you already know how the frame size, this letter combination, is related to the actual dimensions of the converter. That was the table on the previous slide. So what we had here for the inverters or converters: power, rated current, maximum current, and then we have two cases: light overload use and heavy duty use. So what is meant here? So this is the same frequency converter, this line, but if we use it with light overload application like pump, for example, or fan, those applications do not include any overloads at all. So then we can run this particular inverter in this line with the motor which has 0.75 kilowatt power. But if we have heavy duty use, something like elevator or winch or a conveyor, then we should account for only 0.55 kilowatt motor. So you see, we are able to run smaller motor with the same frequency converter. So if we have a motor which is rated 1.5 kilowatt, if we are going to run a pump, then this is the kind of frequency converter we need to choose. If we have conveyor, then we need to take the next one from the next line. Currents of course will be different than in both cases, and then frequency converter will have different rated current. So here we also have designations. At the bottom of the table we can find the explanations of the different symbols we see in the table. So it's useful to read all this information. Just find catalogs online and look them through, read every line, try to understand what is meant by this or that. And now to transformers. This is also ABB, and you can see dimensions of the transformer. This is a vacuum cast coil transformer with protection IP00. That means basically no protection, but in the same catalogs they are transformers with a better protection, IP21 and IP23. And here we have the table with parameters of the transformers. So the main parameters, of course, power, but we also look at the voltage level. So this is the highest voltage the transformer can handle. And basically the transformer can be designed for any ratio between high voltage and low voltage. So here we can see a lot of data, including dimensions and weight of the transformer, as well as losses and some other important parameters. Of course, the transformer catalogs, they include quite a lot of additional information. I just have here one example of what it could be and how it could look like. So for example, connection diagrams and insulation class and temperature class, maximum ambient temperature the transformer can be operated in, and so on and so forth. Here's the table from Trafotec catalog. Trafotec is the transformer provider, and we can see here that this transformer is built for voltage ratio, or bringing voltage down from maximum 7,200 volts down to 400 volts. And the price of this transformer will be a little bit different depending on the production class, IP23 versus IP00. And we see motor power, which could be the motor could be run from this transformer. And we also see the transformer can be a little bit different configuration, 6 poles and 12 poles. So again, in DriveConstructor textbook you will find the details of this. Okay, this is the last slide of part number 2 of our lecture. So thank you for watching, and I'm inviting you to watch part number 3. Thank you.